Hello. So this is the first online lecture we'll have for our natural disasters course, and it feels kind of weird because obviously this whole situation is weird, but I saw you guys in person 2 weeks ago, and then it was like, oh, I'll see you after spring break, and then boom, the pandemic hit. Sounds like a movie or something, right? But so for the time being, we'll be remote, and we don't know how long that'll be for. It could be 2 weeks, it could be who knows how long. But you will find your lectures on your Blackboard site under the online lectures tab. The homework is, as you know, on Blackboard. Our future exams will be on Blackboard. I still have to enter your grades for exam 1 on Blackboard. I'm a little behind that, and I apologize. And yeah, so that'll be it for the course. I have also a question and answers tab on the left-hand side that bring you to a forum where you can post questions you have about the content of the course, so I can answer them, so that other students can see your questions and the answers as well. If you have other type of questions that aren't related to the content, then you can send me an email. Make sure you include GEO 1030 in the subject line, because I receive a lot of emails. Make sure I find it in a timely manner. So with all that said, I just want to put a little disclaimer out there that I'm making these lectures from home, right? Because everyone should be at home. But that means it's an uncontrolled environment. So for example, I have, well, let me show you. I can't do that. So I have right now, I have a dog right there, and I don't know if you can see, I have a little girl on the couch right there. Having a hard time sleeping, so she's sleeping on the couch while I do this. So who knows what kind of interruptions we have during the time. Hopefully both of them stay as is for the time being, but if there are any eruptions, I ask you to please excuse me. It's just the nature of what we're doing here. Okay, so all that said, we will pick up where we left off before spring break, and that was talking about volcanism. So I'm going to share the PowerPoint slides here. All right. So we left off, we're talking about the nature of volcanic eruptions. We talked about how, most people, they think of Vesuvius and Pompeii, think about volcanism as a natural disaster. And that was obviously an explosive eruption, but not all eruptions are explosive. So eruptions, volcanic eruptions exist on a spectrum from very explosive and violent to very effusive or peaceful. So, as we said, for example, Mount St. Helens eruption in 1980 in Washington State is an example of a very explosive eruption. You can see what it did to this landscape. And I think I remember showing you the Google map images of all the trees blown down and the trees that have washed into the lake in the foreground in the bottom picture. Where volcanic eruptions can be very effusive or peaceful, like this one in Kilauea of Hawaii. If they were afraid that this volcano was going to blow up the way that Mount St. Helens did, then we'd be flying a volcano next to it. Flying a volcano. Flying in helicopter next to it, as you see them there. So what determines the type of eruption that a volcano exhibits? Well, there are several factors that influence nature of volcanic eruption. They are the viscosity of the magma and the amount of dissolved gases in the magma. And so first, we're going to start with the viscosity of the magma. What influences viscosity? and what influences the viscosity of magma. So first of all, what is viscosity? Well, viscosity is the internal resistance to flow of a fluid. So if a fluid has a high viscosity, it has a large internal resistance to flow. It doesn't want to flow, it kind of creeps. Where if a fluid has a low viscosity, it has very little internal resistance to flow and it flows very easily. So let's see if this loads. So you can see here water on the left-hand side. It's a very low viscosity, flows very easily. Where corn syrup, it doesn't. We try to pour the two out. Water, being very viscous, flows very easily. Where corn syrup, having high viscosity, unlike water, it creeps out. It's much more, you can think of it as being thicker. All right, so this is corn syrup being very viscous and water not very viscous. Okay. Let's see. That's viscosity. And so what influences the viscosity of magma? Well, there's two factors that influence the viscosity of magma: the chemical composition of the magma and the temperature of the magma. First, we're going to look at the chemical composition and how that influences the magma. So of the 92 naturally occurring elements in Earth's crust, misspoke. Of the 92 naturally occurring elements in the universe, only 8 of them make up 98% of Earth's crust. 12 of them make up 99.23% of Earth's crust. So there's a lot of elements that exist, but very few of them are actually found in large abundance in the Earth. And with oxygen and silicon being the most abundant, the two most abundant elements. In oxygen and silicon, they bond together to form this structure called the silica tetrahedra. So this SiO4, that's called silica, and it bonds in a way that the 4 oxygens bond to 1 silicon. That's why you get the Si with no subscript. It's an inferred 1. So Si1, 1 silicon atom, and O4, 4 oxygen atoms. And that's how these 5 atoms bond together, and it forms a structure called a tetrahedron. Tetra, 4, hedron, face or sides. So it's this 4-sided polygon, with this being 1 side, 2, the bottom here is 3, and then this back side, this back side right here behind here, that's 4. That's the 4th face. You can do it right here. 1, 2, 3, and then the back one there is 4. So that's why it's called a tetrahedron. So this is the most, you can think of this as being the building block of rock, okay? Because silicon and oxygen are the 2 most abundant elements in Earth's crust, and this is the structure they form. They bond together. Now these silica tetrahedra, they like to bond to other silica tetrahedra, and so they're attracted to each other. So as a result, the more silica it's in the magma, the more internal attraction between the silica tetrahedron. And the more internal attraction between these silica tetrahedra, that creates a larger viscosity, because they don't want to move relative to each other. They want to stick to each other. So therefore, if a magma has a high silica content, has a lot of silica in it, it's going to have a larger viscosity. Where if there's a lower silica content, the magma is going to have a smaller viscosity. Okay, so more silica, more viscous. Less silica, less viscous. There's 3 different types of magmas that exist on Earth: basaltic, andesitic, and rhyolitic. Basaltic has 50% silica, andesitic has 60%, and rhyolitic has 70%. And so for this reason, basaltic is the least viscous. If you can read this. And felsic, having the most silica, is the most viscous. And intermediate, or in between, is this andesitic. magma. It's more viscous than basaltic, but less viscous than rhyolitic. So that's how the chemical composition of magma influences its viscosity. The other factor that influences the viscosity of magma is its temperature. So I don't know, maybe you've heard this phrase, molasses in January. So if you're moving slow, someone might say, oh, you're moving as slow as molasses. Because molasses is a very thick syrup. It's very viscous. It flows very slowly. If you're moving really slow, someone might say you're moving as slow as molasses in January, where what's inferred in there is that in January it's cold. So cold molasses flows even slower. So in that saying, if you've heard of it, we have the temperature dependence of viscosity in there. So cold molasses is much more viscous. It flows more slowly. So in general, as a fluid cools, it becomes more viscous. So the lower the temperature, the higher the viscosity. Okay. We can see that demonstrated here. We don't need the sound. So what we do is they drop a honey in cylinder, they drop a marble in cylinders of honey. And you can see now this cylinder has 50-degree honey in it, while this cylinder has 100-degree honey in it. And the less viscous the honey, the more easily it can flow off underneath the marble and allow the marble to sink. So this honey, being cooler, should be more viscous, and so it should take longer for this marble to sink because the honey has a harder time flowing off underneath the marble. Whereas this honey, being warmer, this marble should sink more quickly because the less viscous honey can more easily flow off underneath it. And as we can see, this marble is sinking much more faster than that one. And if we replace this 100-degree honey with 70-degree honey, see that this marble sinks faster than the 50-degree honey, but slower than the 100-degree honey. So, and there we see the temperature dependence of viscosity. So of the three types of magma, rhyolitic exists at the coolest temperatures, andesitic at higher temperatures, and basaltic at the highest temperatures. And so for this reason, rhyolitic being the coolest, it has a higher viscosity, and basaltic being the warmest, it has a lower viscosity. So for both reasons, both the composition and the temperature, basaltic is the least viscous. It has the least amount of silica and exists at the highest temperatures. Where rhyolitic magma is the most viscous because it has the most silica in it and it exists at lower temperatures. Okay, so here's a summary. Basaltic magma has a lower silica content, high temperature, so it has the lowest viscosity. Rhyolitic has high silica content, low temperature, and therefore has the highest viscosity. And intermediate, andesitic magma is intermediate, it's in between. And so it has an intermediate viscosity. All right, so going back to the factors that influence the nature of volcanic eruption, the viscosity is one. The second is the amount of dissolved gases in the magma. Okay, so when we look at the amount of gases, we have to think of something called gas solubility. So gas solubility is how much gas can be dissolved in a liquid. Now, a common example of this is a beverage that's carbonated, because carbonation is carbon dioxide dissolved into water. And we typically keep soda under pressure, so with the lid on, and at cool temperatures, because the gas solubility, the amount of gas that can be dissolved in a liquid, increases with lower temperatures and higher pressures. So if we look at gas solubility on this axis, let's say temperature on that axis, same thing here, gas solubility on this axis, and pressure on this axis. The lower the temperature, the higher the gas solubility. And as you increase the temperature, the gas solubility decreases. And conversely, higher pressures have higher gas solubility. And as you lower the pressure, the gas solubility decreases. So that's why if you take the lid off of a soda, what happens is you hear that pressure release. Once that pressure is released, what begins to form? But gas bubbles in the liquid, because gas bubbles are undissolving out of the liquid because you decrease the pressure the liquid is under. So you decrease the pressure, and therefore you decrease the gas solubility. So it can't hold as much dissolved gas, and so gas begins to undissolve, forming gas bubbles. Also, we keep soda cold because colder water can hold more dissolved gas. A warm soda goes flat much faster than a cold soda because that warm soda has a higher temperature, therefore has a lower gas solubility, so the gases escape more quickly. They undissolve out of the liquid more quickly, where a cooler soda has a lower temperature, has a higher gas solubility, and they can hold on to its gases longer. They dissolve out more slowly. Okay, so in summary, how does the amount of dissolved gases change with pressure? So the higher the pressure, the more dissolved gases there will be, and the lower the temperature, the more dissolved gases there will be. So water is the most abundant dissolved gas in magmas. Now, as magma rises and comes near the surface, it's under less and less pressure, because remember, pressure increases with depth. So as magma comes closer to the surface, pressure it's under decreases. A decrease in pressure lowers the gas solubility of the magma. And so what happens is the gas that's dissolved in the magma, water, begins to undissolve out, forming water vapor bubbles, so steam bubbles. Okay, and basaltic magma, having high temperatures, because it's the highest temperature, it has a low gas solubility. It can't hold a lot of dissolved gases, so it has a low water content. And so that small amount of water vapor bubbles can easily move through the low viscosity basaltic magma. And so it results in very peaceful, safe eruptions. So a good analogy is this is like a soda bottle. If you shake it up, a bunch of CO2 undissolves and it builds pressure inside the bottle. Now, if you take that lid off, all those CO2 bubbles that form, they want to escape really quickly. And so they come rising up to the surface to go from the high to low pressure, which is outside the bottle. Those CO2 bubbles, they move so quickly that they bring the liquid out with them. And so that's what makes the soda bottle erupt, is those CO2 bubbles wanting to escape the liquid and coming out so quickly that they bring the liquid out with them. That is exactly what happens with volcanoes with basaltic lava. What brings the lava to the surface? It's the pressurized gas wanting to escape, and that gas escaping to the surface and bringing the liquid out with it. Rhyolitic magmas, on the other hand, are much lower temperature, so they hold more dissolved water in them. So as they come closer to the surface, many more steam bubbles form. And rhyolitic magma has a much higher viscosity. So those steam bubbles that form, they have a hard time. They cannot escape through the very thick and viscous rhyolitic magma. And so they build pressure, and they build pressure, and they build pressure until finally the rock that's over above atop the magma is no longer strong enough to hold all that pressure in. And it finally just, boom, explodes. And all of the rock that's over top gets blasted out, and all of that pressurized magma just, boom, it just fragments, it explodes. And it sends fragments of molten rock flying through the air, very frothy molten rock with a bunch of gas bubbles in it. And so this is what creates these very explosive, violent, dangerous eruptions. It's because of the high dissolved water content and the high viscosity of rhyolitic magma. Or basaltic magmas have more peaceful eruptions because they have much less water in them, and the magma has a low viscosity, allowing what water is in it to easily escape. So I don't think this is going to work on this computer, but this is just a video showing that this is corn syrup, of how gas bubbles have a hard time escaping through the thick fluid. It compares corn syrup to water. You can see how the water can escape, the gas bubbles can escape the water much more easily than they can the corn syrup. So this table summarizes the three types of magma: basaltic, andesitic, and rhyolitic, and talks about its silica content. So basaltic has the least, andesitic has in the middle, and rhyolitic has the most. The temperature: basaltic has the highest temperature, rhyolitic lowest temperature, andesitic in between. Viscosity: basaltic having a low silica content and high temperature has the lowest viscosity. Rhyolitic having a high silica content and low temperature has the highest viscosity. Amount of dissolved water, because basaltic magma has a high temperature, has a low amount of dissolved water. Because rhyolitic magma has a low temperature, has more dissolved water. And the gas escape from magma, because of the low viscosity of the basaltic magma, the gas can easily escape. But with the high viscosity of rhyolitic magma, the gas has a hard time escaping. And this results in the small amount of water that can easily escape. The less viscous magma results in peaceful eruptions, where the larger amount of water having a difficult time escaping the more viscous rhyolitic magma results in explosive eruptions. So, where do volcanoes occur? Well, we understand where and why volcanism occurs in the context of plate tectonics. So 90% of all volcanism on the planet occurs at plate boundaries. 80% is at mid-ocean ridges, spreading centers, which are at the bottom of the sea floor, and they go pretty much completely unnoticed by us. Where 10% occur at subduction zones. Now, this 10% at subduction zones, that's the volcanism that most people think of when I think of volcanism, as we'll talk about. And the remaining 10%, so this is the 90% that's at plate boundaries. The remaining 10% is not at plate boundary as a result of hotspots, which are mantle plumes, which we'll discuss a little bit. So divergent plate boundaries and volcanism. So mid-ocean ridges are divergent plate boundaries on the sea floor, and there is extensive volcanism here. So this the lithosphere is very thin here, and right close to the surface, these divergent plate boundaries, is the very warm asthenosphere rock. The asthenosphere has very low silica content. So as the plates pull apart, the asthenosphere moves closer to the surface, where it actually melts because the rock is under lower pressure. So the rock doesn't melt because it's heated up. It melts because its pressure is decreased, okay, as it comes closer to the surface. So as that rock melts, it changes to high temperature, low silica content, low dissolved water, low volatile content, and low viscosity basaltic magma. So all those factors result in a very peaceful eruption. Okay, the low silica content and high temperature make it result in a low viscosity, and then the low volatile, or the small amount of dissolved gases, make it even less explosive. And so we have these very peaceful eruptions at these divergent plate boundaries along mid-ocean, these mid-ocean ridges. So the eruption of this basaltic lava, it cools and forms basalt, which is the rock that makes up the sea floor, forms new sea floor at these mid-ocean ridges. So the lava cools to form the volcanic rock basalt. It's the most abundant rock on the sea floor. And so this is the rock that forms from that low viscosity, low water content, very peaceful, effusive eruptions. So it's like lava oozing out at the bottom of the sea floor, cooling quickly to form that rock, which is the rock that makes up the sea floor. Subduction zones, on the other hand, are a different story. So the subducting oceanic lithosphere takes water down into the Earth's mantle. Okay, this water is then released by the rock. Whenever it gets warm enough, it undergoes these chemical reactions, and the water is released and it moves into the overlying mantle rock. And when this rock is infused with water, it causes this rock to partially melt. Okay, and that partial melt forms magma, and then that magma rises. As it passes through the continental crust, it melts that continental crustal rock, changing its composition. So the more continental crustal rock it melts, the less basaltic it is. It becomes more andesitic and more rhyolitic. And so it's transforming from the magma that results in peaceful eruptions, basaltic, into the more explosive eruptive forming magmas, andesitic and rhyolitic, as it melts through the continental crust. So as a result, the formation of this andesitic and rhyolitic magma results in explosive, violent eruptions along subduction zones. All right, so as we said, magma is generated by the partial melting of the mantle above the subducting plate. Down here, the melt rises and it melts, the magma rises and it melts the overlying crust and changes the composition of the magma from basaltic to andesitic or rhyolitic. So the magma temperature decreases, becoming more viscous, while it increases in silica content, which also makes it more viscous, and it also absorbs more water. And all of these factors play into much more viscous, much more explosive magma. And so all that water, it begins to undissolve out of the magma. It can't escape this more viscous magma, and so it builds pressure until there's enough pressure, it blows out, and you have a volcanic eruption, an explosive volcanic eruption. So their subduction zone volcanoes are explosive and dangerous due to their high viscosity and large gas contents of the magma involved in them, the andesitic and rhyolitic magmas. And so these subduction zones, they can last for tens of millions of years. And so the volcanoes along these subduction zones, they can become active at any time. And then they can lay dormant for centuries. So they're very unpredictable, which makes them dangerous. They can be active, very active for a number of years, and then just go dormant for hundreds of years, and then become active again. They go dormant for a short period of time, and then become active again. So they're not necessarily periodic or have a set frequency, which is different from earthquakes. Earthquakes tend to have a more periodic nature to them, unlike volcanoes. So andesitic and rhyolitic lavas, whenever they erupt, they don't form basalt, they form different types of rocks. Andesitic lavas form the rock andesite, and rhyolitic magmas form the rock rhyolite. And so these materials are formed as the basaltic magma moves up through the mantle, and it begins to move into the continental crust, melting that crustal rock, which causes it to incorporate more silica, because continental crust is made up of silica-rich rock. And so as it rises and obtains more and more silica, it transitions from basaltic to andesitic, and eventually it could become rhyolitic in composition before it erupts. So how a volcano erupts? So we begin at depth, right? So rock that is heated deep in the mantle has a lower density because of thermal expansion. Because as you warm things, they expand, become less dense, and begins to rise. In this process of warm, less dense materials rising and cool, dense materials sinking, it's called convection. So as this hot mantle rock rises, remember the mantle is very warm, so it's plastic, so it can deform and flow like a fluid on long time scales. So that's how this rock is rising. Excuse me. So as this rock rises, it's under less and less pressure, and that results in the rock eventually causing it melting because of the decrease in pressure. And then as it melts, the gas bubbles begin to form because it decreases in pressure even more as the magma moves closer to the surface. And the pressures build, and that pressurized gas propels it to the surface, which eventually leads to the magma to the surface, which eventually leads to an eruption. So 3 things can cause rock to melt. We can lower the pressure of the rock, like we talked about above. We can raise the temperature, which is the most obvious one. We can also increase the water content. That's what happens at subduction zones. As we go back here, the oceanic crust takes water down into the mantle. That water is released, and that water added to the mantle rock here causes it to partially melt. And so lowering the pressure of rock is the most common way to melt it, and that occurs above divergent plate boundaries. So you have, 2 plates. This is the lithosphere. They're moving away from each other because they're driven by this convective upwelling in Earth's mantle. And this mantle rock rises towards the surface. And as it rises to the surface, as it's convecting, it decompresses. And it gets a low enough pressure where it begins to partially melt, and that melt rises to the surface and erupts. So magma at depth is under too much pressure for gas bubbles to form, just like the soda with the lid on. Okay, but as it rises towards the surface, it's under less and less pressure. The gas solubility decreases, and so gas bubbles begin to undissolve out and gas bubbles form. And those gas bubbles, once they're formed, as the magma moves even closer to the surface, it's under less pressure, these gas bubbles want to expand, which pressurizes the magma from within, and that internal pressure propels the magma further upward, either moving it into already existing cracks or causing it to crack the rock above and then moving up into those newly formed cracks. And eventually, so many gas bubbles form, and there's so much pressure that they overwhelm the magma, causing it just to explode, fragment into pieces as it erupts. And that forms what's called volcanic ash. Ash is formed as the magma. It doesn't come out as a liquid. It just completely blasts apart into tiny fragments that move up into the air and cool, forming this volcanic ash. And then you have the gases coming out, pressurized gases propelling that ash that's being erupted up into the atmosphere. So there are various different styles of eruption, and they all have to deal with how much water, basically, and also partly what type of magma. So the concentration of water is the primary factor in determining whether magma results in a peaceful or explosive eruption. So basaltic magma, even though it has a low viscosity, if it has enough water in it, which is hard for it to have a lot of water in it because it's so warm, it could be explosive. It just doesn't happen very often. And rhyolitic magma usually has a lot of water in it, and it's very viscous, which results in it being explosive. So we have various different types, styles of eruptions that exist. We have non-explosive, Icelandic, and Hawaiian styles, somewhat explosive, Strombolian styles, and then the more explosive Volcanian and Planaean style of eruptions. So looking at volcanic materials that come out of a volcano, we have a low water content, low viscosity, very peaceful eruptions. We have these lava flows. And we have different types of lava flows. Pahoehoe and Ah, those might sound like funny terms. Those are Hawaiian, so that's why they might sound a little foreign to us. They refer to lava flows 2 different locations from the opening of the volcano, the vent. Ah is this rough, blocky surface. Those are lava flows much further from the vent, the opening of the volcano, and so the lava has begun to cool and form rock, and the lava behind it pushing it causes that newly formed rock to break and fracture, forming this rough, blocky surface. Or Pahoehoe, those are lava flows much closer to the volcano, so the lava is much warmer, and flows more easily and creates a smooth, ropey surface. And pillar lavas are structures that form whenever lava actually erupts underwater. It flows a little bit, solidifies, and forms up like a pillow shape. Those are the different lavas, type of lava flows. Then we have pyroclastic materials. These are particles or objects that are erupted into the air. Going from smallest to largest, we have this really fine volcanic ash or dust, the size of flour. It's very, very easily carried by the wind. It's very harmful. And coarse ash, they're very harmful to your respiratory system. You inhale those, and they just wreak havoc on especially your lungs, your bronchioles. And you have cinders, marble to baseball-sized fragments, blocks, which are big fragments, solid while airborne. Volcanic bombs, they're large fragments of liquid while airborne. Volcanic tuff, rocks made of smaller fragments that are welded together during the eruption. And then you have volcanic breccia. This is rock made of coarse angular fragments that they're usually deposited by water carrying debris and depositing them. And then you have volcanic glass, obsidian, pumice, where obsidian is non-porous glass. It has very little gas bubbles in it, and pumice is very porous glass, has a little bunch of gas bubbles in it, makes it look frothy. So these are glasses because the molten rock cools so quickly that mineral crystals don't develop, and so it forms into a glass. So here's some pictures. This is the Pohoihoi has a smooth, ropey texture, or this rough, jagged texture. That's the So this is much closer to the vent of the volcano, where the lava is coming out, and this is further from the vent. Pyroclastic debris, you have is ash, so it can be deposited ash fall. So there's layers that set off from ash cloud. And you can also have pyroclastic debris that's ejected very violently out of a volcano. That's known as a pyroclastic flow. So ash fall is never the ashes in the atmosphere, and it slowly settles out and accumulates. Where pyroclastic flow is never a volcano erupts, and a huge rush of pyroclastic material is blasted out and flows down the side of the volcano. And then we have obsidian and pumice. Obsidian is known as volcanic glass. Pumice, you might have seen it's commonly used for exfoliating. Right? It's very light rock because of all the gas bubbles. It makes it very abrasive. These both form from very rapid cooling of molten rock, those pyroclastic materials. So the 3 V's of volcanology: viscosity, volatiles, and volume. The combination of these 3 determine the type of volcanic eruption that exists. So the viscosity can be low or high, and that controls whether the magma flows easily or piles up, and how easily the gas bubbles can escape from the magma. The volatiles, which are dissolved gases, the abundance of them, if it's low, medium, or high, determines if the magma will just slowly ooze out if there's a low gas content, or if it'll just explode if there's a high gas content, which builds a lot of pressure. And the volume of magma involved can be very small, so small amounts of magma, medium or large, and as you might guess, the greater the volume, the more intense the eruption. So a quasi-quantitative scale in which we rank the how explosive volcanoes are is the Volcanic Explosivity Index, shortly known as the VEI. So this provides us a means of evaluating eruptions according to a couple different parameters. It's the volume of material erupted, the height of the eruptive column, so how high material is erupted up into the atmosphere, and the duration of the major eruptive blast, so how long it erupts for. And the VEI scale ranges from 0, being very peaceful, to 8, being extremely explosive. So down here, we can see the VEI. we have the volume of material ejected, eruptive column up into the atmosphere, the height in kilometers, and we have the eruption style. And this is, we'll look at different eruption styles, and this is the duration of the blast in hours. So the more peaceful ones, Hawaiian is a very low volume, low eruptive height, and very short-lived eruptions. A little bit more explosive ones, like the Strombolian, has slightly more volume, erupts higher into the atmosphere, and it might last a little bit longer. Volcanic, a little bit more explosive. They include higher volumes, and erupt material higher into the atmosphere, and they can last for longer periods of time. And Planaean, the most violent type of eruption, they can range anywhere from 4.5 up to an 8 on the VEI. They erupt large volumes of material, very high into the atmosphere, greater than 25 kilometers up into the atmosphere, and they last a long time, last around 12 hours or half a day. So those are how the 3 V's, the volume, the volatiles, and not the 3 V's. That's how how we determine the VEI. It's the material erupted, height of the eruptive column, and the duration of major blast. And the VEI helps determine is determined by those 3 V's we talked about earlier: the volume, viscosity, and volatiles. So we can see by different combinations of these 3 V's, we get different types of eruptions. Okay, so we can look at these. If we have low viscosity, low volatiles, and a large volume, that results in the formation of shield volcanoes or flood basalts, which are very peaceful or effusive volcanic landforms. So Hawaii is an example of a shield volcano. So it's produced by the eruption of the low viscosity and low volatile basaltic magma, but large volumes. It's basaltic lava. It flows far distances before it cools, and so it forms this very broad-shaped structure, which if you look at it, it's this broad dome-straight shape that kind of resembles a warrior's shield. So a very large volume of lava being erupted, but very peacefully. So there's just thousands of layers of lava flows on top of each other, and that's what creates this structure. So inside of it, it's just layer after layer after layer of lava flow, and it's much, much, much wider than it is tall, because of that low viscosity of the basaltic lava, allowing it to flow far distances. And so you can see these Hawaiian type eruptions, very, very peaceful, but the lava can flow far distances. And there can be a large amount of lava from eruptions that last for days or years. And so these volcanoes are usually not threatening to life because lava doesn't flow that fast that you can't get out of the way, but it's hard to move structure, right? So structures and roads are often can be destroyed by these lava flows. So they're not threatening to life, but they are threatening the property. Lava flows. Icelandic type eruptions, like those that we see in Iceland, are the most peaceful eruption type, even more peaceful than Hawaiian. And so these form in Hawaii, it's on a divergent plate boundary, or in Iceland, on a divergent plate boundary, where the rock is being pulled apart, creating cracks, and the lava erupts through its cracks, forming these fissure eruptions, where the lava erupts out of these linear vents that can run many kilometers long, creates this curtain of fire effect. But there's very low viscosity, low volatile basaltic lava that flows so easily that it almost forms these flat structures like a volcanic plateau. So it's even more broad than shield volcanoes, these nearly horizontal layers of basalt. If we have the same low viscosity and low volatile basaltic magma, but with extremely large volumes, that creates these volcanic events known as flood basalts. And these are the largest volcanic events known to occur on the planet, and they've only occurred a handful of times. they last for a long time with regards to human timescales, millions of years. They're very short, geologically speaking. So these volcanoes are up for 1 to 3 million years. And they, so water vapor is a volcanic gas, but also carbon dioxide and sulfur dioxide are common volcanic gases. And so much lava comes to the surface because the volume is so large that a large amount of carbon dioxide and sulfur dioxide are released into the atmosphere. And and that so much carbon dioxide is put into the atmosphere that it actually causes the atmosphere to warm. And historically, we've seen this happen in Siberia 250 million years ago. 3 million cubic kilometers of basaltic lava erupted, and it brought enough CO2 to the atmosphere to significantly warm the climate, and that CO2 dissolves into the ocean and causes the ocean to acidify. And that warming of the climate and acidification of the ocean over the course of those couple million years, 1 to 3 million years, was rapid enough that evolution could not keep pace, and many species went extinct, resulting in the largest mass extinction in Earth's history. It was known as the Permian-Triassic mass extinction. This one that happened in Siberia 250 million years ago. Paleontologists refer to it as the Great Dying. And 65 million years ago, this happened in India as well. It happened to coincide also with the meteorite impact. So it brought about the Mesozoic mass extinction that didn't work out well for the dinosaurs, but there was a 1-2 punch with this volcanic event, these flood basalts in India, and the meteorite impact. But we can learn from these flood basalt events, especially this one that happened 250 million years ago, because we saw that by increasing the amount of CO2 in the atmosphere, it increases the greenhouse effect, causes the climate to warm. Also, the CO2 dissolves into the ocean. When you dissolve carbon dioxide into water, it creates carbonic acid, which makes the water more acidic. And so that warming of the climate and acidification of the ocean over the course of a couple millions of years was just detrimental to life on Earth. And many, as I said, species went extinct. Now we're seeing that now today, but it's a different process, not volcanism. It's us exhuming fossil fuels from the Earth in the form of coal, natural gas, and oil, and then burning them, and that releases carbon dioxide. And we're seeing the same process occur today. So we're increasing the amount of carbon dioxide in the atmosphere, increasing the greenhouse effect, causing the climate to warm, and also that CO2 is dissolving into the ocean, making it more acidic. Actually, when we started burning all these fossil fuels, starting in the 1750s with the onset of the Industrial Revolution, since then the ocean is 33% more acidic in just those 250 years. And so we're seeing what happened in the Permian-Triassic mass extinction, largest mass extinction in Earth's history. We're seeing it happen now, the same thing. The only difference is it's happening at a much faster rate today, where this CO2 was being burped into the atmosphere from this volcanism over the course of 2 to 3 million years, where we're releasing similar amounts of CO2, but over the course of hundreds of years. So the geologic record tells us what to expect. The fossil record tells us what to expect. So there's no doubt about it, what's going to happen if this continues. And extinction rates today are already high enough to qualify as the mass extinction. So we are currently in a mass extinction. We're actually in the 6th mass extinction of Earth's history. And this one is, likely due to our activity, which the good news is we can reverse it. But I just talk about this because it ties into, you hear people talking about global warming, climate change today. Well, there actually is a precedent to it. There are natural processes that we can look back to and see what to expect. Right? And so the thing is, Earth has been much warmer in the past than it is today. That's fine. It's just that when the climate changes too quickly, life can't adapt quick enough, so it goes extinct. So moving on, if we have low to medium viscosity, but a higher amount of dissolved gases, medium to high, and a small volume, it creates these things called scoria cones. So scoria cones are these very short-lived volcanic features. They're also known as cinder cones, and they form several eruptions over the course of several hours. They form these little tiny, these relatively small structures, and then they go extinct. We don't know a lot about these volcanic structures. They typically form along subduction zones. So there's still more to learn about these. And also, from the similar combination of low to medium viscosity, medium to high volatiles, and small volume, we get Strombolian type eruptions. Okay, so these Strombolian type eruptions are named after Mount Stromboli, Italy, and it erupts almost daily for thousands of years, which is a tourist attraction, but it's kind of like just spitting out small amounts of pyroclastic material. A similar volcano in Michoacan, Mexico, except this one formed over, it just there was a farm field, and then a scoria cone just formed as this volcano started erupting, and it built its structure up over the course of 9 years, burying the area and destroying 2 towns around it. So these come into existence very quickly, and they go extinct. Looking at medium to high viscosity, medium to high volatiles, and large volume results in stratovolcanoes. Now, stratovolcanoes I like to call your stereotypical volcano, because whenever you ask someone to imagine a volcano, this is usually what they imagine. This is what comes to mind. So these large steep slopes, a high altitude, so it has the ice cap, right? So they're composed of alternating layers of pyroclastic debris and andesitic or rhyolitic lava flows. So unlike shield volcanoes, which are just layers of lava flows, and scoria cones, which are just layers of pyroclastic material, these stratovolcanoes are made of alternating layers of pyroclastic material and lava flows. So what happens is there's an explosive eruption which blows out pyroclastic material. That pyroclastic material settles on the flanks of the volcano. And then following that, there's lava flows that float over it, forming a layer of rock. And so the strat, in the word stratovolcano, means layered. So that's how they get the name stratovolcanoes. They're also known as composite volcanoes because they're made up of a composite of pyroclastic debris and lava flows. And so stratovolcanoes, they exhibit both Volcanian to Planaean type eruption styles. They usually exhibit both. And so Volcanian type eruptions, they alternate between very viscous lava flows and pyroclastic eruptions. And a Volcanian type eruption is usually the first eruptive phase of a stratovolcano. It's basically the mountain blowing its top off. It's commonly referred to as the clearing of the throat phase. So just you have just this pyroclastic material just blast out. Maybe some very viscous lava come out as well. But once the top is blown off from the Volcanian phase, then the Planaean phase begins. And this is the main eruptive phase where the magma the pressurized magma just being blasted out. It's fragmenting as it comes out of the volcano and turning into ash. And that ash is being propelled high up into the atmosphere. So they get their name Planaean, named after Pliny the Younger, who wrote an extensive record of the 79 CE eruption of Mount Vesuvius. And so this Planaean phase occurs after the clearing of the throat, the Volcanian phase, and it's commonly the final eruptive phase. And so the very pressurized gas, it powers these large vertical columns of pyroclastic debris up to heights as high as 50 kilometers into the atmosphere. So Mount Vesuvius in 79 CE is result, it was formed along the subduction zone of the Mediterranean seafloor beneath Europe. And for the most 4,000 people who remained in Pompeii during the eruption were killed by thick layers of hot pumice and pyroclastic material from the first Volcanian type eruption, where the mountain blew its top off. It actually blew its top and part of the side up. And that blast sent a bunch of pyroclastic material flowing down and overcoming Pompeii. So today, using seismic waves, we can image the subsurface. We can see there's a 400 square kilometer area magma body of magma 8 kilometers north of Vesuvius. And there's, as we said, there's many people living in that area, the Bay of Naples area. So that volcano will likely erupt again in the future. And hopefully we don't have a Pompeii 2. So here's Vesuvius. And you can see these numbers here are how thick the volcanic ash was. This is the pumice fallout. You can see here's Pompeii. You have 200 centimeters of volcanic ash were deposited. That's 2 meters. It's a lot of ash. So Pompeii was right in the blast zone. So you see the mountain blew its top and it blew out this side. So it just, all this volcanic material was just blasted out in that direction. Or on the other side, Herculaneum was another town, was destroyed at the time. It was destroyed by something else, not pyroclastic flows. It was destroyed by lahars, which we'll talk about. So the next structure we'll look at is results from high viscosity, low amount of volatiles, and a small volume. This is called lava dome. So a lava dome is just very, very thick, low gas content, very small amount of magma that just kind of lurches up at the end of a volcanic eruption. And it kind of just moves up in there and it stops near the top as it cools and solidifies, and it forms this thing called a lava dome. And so once this lava dome hardens, it acts as a plug. It's sealing up the volcano. And as it forms and cools and solidifies, it's creating the lid that's going to allow the pressure to accumulate for the next volcanic eruption. So it's the final phase of the typical sequence of a stratovolcano. The stratovolcano has the Vulcanian phase, where it blasts open, the Planaean phase, where it's erupting up into the atmosphere, and then the lava dome phase, where all the gases escaped and this very low pressurized magma just creeps up and it solidifies, sealing the volcano up. So as I mentioned, the typical eruption sequence of a stratovolcano, gas-rich materials shoot out first in the Vulcanian blast, followed by the longer Planaean eruption. After the gas is depleted, the high viscosity magma builds a lava dome over a long period. So we have this Vulcanian precursor, the Planaean main event, the lava dome conclusion. And finally, if we have a high viscosity, a large amount of volatiles, and a very large volume, we form these things called calderas. So calderas are basically, they get their name from cauldron, which is the large black pot witches stir, because there are these large depressions in Earth's surface. So calderas are large volcanic depressions formed by the inward roof collapse into a partially emptied magma reservoir of an existing volcanic structure. Or they can form by another way, a third way, where the large body of magma in continental crust, as we'll talk about. So 2 ways in which a caldera can form is the collapse of a shield volcano or a stratovolcano into the vacated magma chamber after an eruption. So the idea is, after a large eruption, magma in the magma chamber gets erupted out, it's vacated. So after the eruption, there's this portion of the magma chamber that's empty. And then the volcanic structure then collapses into that vacant space, creating a depression, known as a caldera. Excuse me. So there's been very large ultraplanaean eruptions, say at stratovolcanoes like Mount Toba on Sumatra 74,000 years ago, that created a large caldera, 30 by 100 kilometer caldera. And then often calderas, parts of it will rise up as magma moves up into the volcano and creates these parts of the land that rise up, known as resurgent domes. So here's examples, other examples of caldera. So this is Crater Lake in Oregon over here. This was a large stratovolcano that never erupted. It blasted off its top, but it vacated its magma chamber, and so the structure collapsed down in, forming this large depression. That depression, known as a caldera, is filled in with water. It's known as Crater Lake. And there's a resurgent dome. The volcano began to form again. It's known as Wizard Island. And here, whenever this volcano in Indonesia erupted, Krakatoa, there's a volcanic island. Oh, this is Krakatoa. Sorry, it's Santorini in Greece. Krakatoa, this was the volcano. Whenever it erupted, it collapsed down in, and it's forming this caldera. Here in Santorini, whenever it erupted, it collapsed, forming this caldera. So here's, as I said, Crater Lake. There's a stratovolcano, Mount Mazama, erupted about 7,600 years ago. A major eruptive sequence of pyroclastic flows and planae columns made ash layers that were deposited all across North America. A large enough volume was erupted to leave a large voided or vacated space beneath the surface, which resulted in the structure of the mountain collapsing down into empty space, forming this caldera. You can see the rim here. It's filled in with water since. This is the structure rebuilding. Smaller eruptions have accumulated material, forming this resurgent dome called Wizard Island. So here's a little illustration of what happened. So Mount Mazama is a stratovolcano, underwent a large eruption, vacating a large portion of this magma chamber, which then the structure collapsed down into, forming the caldera. Krakatoa, another caldera formed by this process. It was a stratovolcano formed along the Indonesian subduction-zone. And this volcano was quiet for 2 centuries. It resumed activity in 1883. Moderate volcanic eruptions, a dozen vents, then had a large Planaean blast, erupted material up to 80 kilometers high into the atmosphere. It could be heard 5,000 kilometers away. And so it blew out a 450 meter high island down to a 275 meter deep hole. And that collapse actually triggered a tsunami, which washed ashore nearby Sumatra, actually killed 36,000 people. So it's been building a resurgent dome since 1927. And this eruption is large enough that it actually had an effect on climate. There was enough volcanic material erupted into the atmosphere that it blotted out some of the sun, which actually lowered the temperature, the average global temperature, for a couple of years. So then you have the calderas that are formed by hotspots. So hotspots are wherever these pipe-like upwellings of mantle rock, known as plumes, move from the bottom of the mantle up towards the surface. And they last for hundreds of millions of years. And these mantle plumes, they remain stationary in the mantle as the mantle convects, so they act as a reference for plate movement. So they create volcanoes above them as the plates move over top of them. And so they create new volcanoes in the plate as the plate moves over top. So oceanic hotspots result in peaceful eruptions because the magma can rise easily up through the very thin oceanic crust. So like Hawaii. And hotspots along spreading centers like Iceland are very peaceful as well. However, hotspots that are under continental lithosphere, they create incredibly explosive eruptions because the basaltic magma can't rise up through the continental crust, and so it has to melt up through the continental crust. It has to melt the rock, and by melting that rock, it absorbs all the silica in that continental rock, and it becomes no longer basaltic but andesitic or rhyolitic composition, very And it absorbs a lot of water too. It's very explosive. And it forms a caldera, such as Yellowstone. These are all the different hotspots currently on the planet. Most of them are on oceanic lithosphere, but some from a continental lithosphere, like Yellowstone. And so there's 3 large calderas from this type of volcanism in the United States. So there's the Valles Caldera in New Mexico, Long Valley in California, and Yellowstone, Wyoming. And they occur as large volumes of basaltic magma. They intrude into the shallow depths of the continental rock, of the continental crust, melting it, turning it into a very high viscosity, high volatile, rhyolitic magma that eventually leads to very explosive eruptions. So you can see, this is where Yellowstone is now. You can see how this flat region in here, this is as the plate has moved over top of the plume, the volcanism has blasted all this material out, creating this, basically this plain area. So you can see how the plate has moved over this point in the mantle where the mantle plume is forming the hotspot volcanism. So here is the current Yellowstone caldera. There's 2 resurgent domes where magma in the magma chamber is pushing the land up. And this was an eruption forming a caldera 1.3 million years ago. This is the caldera from the 0.6 million years ago. There's an older one over here that's 2 million years old. If you look at the difference between them, 0.6 to 1.3 is 0.7, and 1.3 to 2 is, well, it's 0.7. So it's about every 700,000 years. And so it's already been 0.6 for 600,000 years. So, Yellowstone could erupt anytime in the next couple 100,000 years. But I wouldn't worry about it too much, because a couple 100,000 years is a long time. Right? So as long as our species has been around the planet, so the chances of it erupting in your lifetime are very, very small. But so these calderas form because this magma body that intrudes into the continental crust, it eventually causes these fractures around the bulge, where then the material erupts out and forms these large clouds of pyroclastic debris that erupt out of these fractures around the magma chamber. And as this magma erupts and is vacated, this land subsides as the magma is erupted out of the magma chamber. And it then forms this depression known as a caldera. So you can see there the formation of the caldera. And then as more magma accumulates, you have the formation of these things like resurgent domes, where the land is pushed up. So we said there was 2 resurgent domes in Yellowstone right here. One resurgent dome, the second. And the magma pushing this overlying rock above the magma chamber, pushing it up. All right, so that's where we're going to leave our lecture for today. So I'll do the second part of the lecture and have it posted for Wednesday. But okay, until then, everyone, stay safe, stay healthy, and stay at home as much as possible. All right, I just have to figure out how to stop recording. Have a good one, everyone.